Thank you for this opportunity to speak at the DPML workshop about the research my students and I are doing on understanding and mitigating privacy risks associated with machine learning. I'm going to talk about some published work, but mostly about very recent and ongoing work with the main goal of getting across what I think is the right perspective for how we should be thinking about machine learning inference risks. The work I'll talk about was primarily done by Bhargav Jayaraman, who's a PhD student in my group leading the work on membership and attribute inference, along with Katie Nittmeyer, who's an undergraduate researcher, and by Anshuman Suri, who's a PhD student leading our work on property inference. Some of the work I'll talk about is also done in collaboration with colleagues at UCLA, Lingxia Wang and Chanchang Gu. It's important to distinguish between two different types of privacy risk in any computation. The first risk is one I'll call data privacy. This is the risk that the inputs, or any intermediate values, are exposed during the computation itself. The second type of privacy risk is inference privacy. This concerns the case where the computation is done as intended to produce some desired output, which is then intentionally revealed. And the risk is that an adversary may be able to infer something sensitive about the computation that produced that output from what was intentionally revealed. In machine learning, the output of the computation is typically a trained model, and the input is often sensitive data collected about individuals and organizations. So data privacy is about protecting that data during collection and training, and inference privacy is about what can be inferred about that training data and the training process, such as hyperparameters used in training, from the released model. The data privacy problem certainly is not solved, and there's a lot of interesting research going on it, especially in distributed settings, like much of the focus of this workshop. But it is well understood. We have well-established formal definitions of our goals. We know how to formalize different types of adversaries, and we have methods for proving when a system achieves certain desired security properties. There are big challenges in making it affordable, but we generally understand what the problem is when we're talking about data privacy. For inference privacy, the story is very different. We have a beautiful and very powerful notion in the definition of differential privacy, and many powerful tools for achieving it, and even some huge and high-profile deployments. But there's a big gap between theory and practice. We can prove theorems that give us very strong guarantees, but the actual privacy loss parameter that we need to make things work in practice, at least for complex learning tasks, is huge. So what most deployments end up doing is using a mechanism that provides a strong differential privacy guarantee in theory, but with a privacy loss budget so high that the actual guarantee is meaningless in practice. The other issue with differential privacy is that it captures a very particular notion of privacy. This is really appealing in the intuitive setting of bounding the risk to an individual of contributing their data to a data set. But it doesn't correspond to all the things we might care about, and I'll shed some more light on that later in this talk. What differential privacy does do is give us a bound on how well neighboring data sets can be distinguished based on the output of a randomized mechanism. Two key points I want to make about this. It's a really general and powerful definition. The mechanism can be anything. Differential privacy is just the definition. For this talk, the mechanism is a machine learning training process that is randomized, and the output is the trained model. The second key point is that the inference bound is strong. It holds in the worst case regardless of what the actual data is and what other information might be available to the adversary. Theoretical computer science is in love with asymptotics and tends to dismiss constants, but here the concrete values are really what matters. The guarantees provided by differential privacy are only meaningful when the privacy loss budget is low. Picking epsilon, the privacy loss budget, that's a policy question. It's a trade-off between privacy and utility. The higher it is, the more privacy leakage, but the less noise that needs to be added to the computation, so hence higher utility. So how do deployments actually set their privacy loss budgets? There are some exceptions, most notably what the US Census is doing, but most organizations pick the privacy budget in a fairly arbitrary way and end up selecting the privacy loss budget as high as necessary to provide the desired utility. As one example, here's what Apple says they do. I don't want to pick on Apple, since it's to their credit they actually publish this. Most companies making claims about differential privacy talk about formal guarantees, but not about privacy utility trade-offs, and not about the actual privacy budgets they select. For learning about the emojis users type, Apple uses a privacy loss budget of 4, enough to give plausible deniability close to 2%. For text predictions, they use a privacy loss budget of 8. I'm not privy to Apple's internal decision-making process here, but my guess is that these budgets weren't decided based on a careful analysis concluding that the choice of emoji is 55 times more sensitive than the choice of text. If there's anyone here from Apple who can shed more light on this in the discussion after the talk, I'd really love to hear it. Differential privacy is just a definition, but the most common way for a computation to satisfy it is to add noise to the output before it's released. To satisfy differential privacy, the noise needed depends on the privacy loss budget and how sensitive the output is to changes in the input. For machine learning, the question is how much a trained model reveals about its training data. We can achieve differential privacy by adding noise to the model parameters after training. For simple convex machine learning, we know how to do this. And many works going back over a decade have been able to achieve differentially private convex learning with low privacy loss budgets using output perturbation. But for complex learning algorithms, including deep learning, we don't know how to compute sensitivity for the whole learning process. Instead, we have to add noise to the gradients at each training iteration. The first attempt to achieve differential privacy for deep learning was 6 years ago. This provided a solid privacy guarantee, but with a privacy loss budget in the hundreds of thousands, so no meaningful privacy. An approach that reduces the privacy loss budget is to relax the definition of differential privacy to allow a small failure probability, known as delta. With epsilon delta differential privacy, the guarantee is that the inference is bounded by the epsilon parameter with at least 1 minus delta probability. According to the definition, the failures can be catastrophic, providing no assurances at all about what leaks when delta is non-zero. But the actual mechanisms that are typically used to provide epsilon delta differential privacy don't tend to have catastrophic failures. These relaxed notions of differential privacy allow for a tighter analysis and replace the linear composition of differential privacy with a sublinear composition. And this has led to some very nice results, enabling what look like fairly reasonable privacy loss budgets for training neural network models, at least in settings where you can start with a pre-trained model, which is what the best results here do. To make this a bit more concrete, here are some results from experiments Bhargav did to understand the privacy utility trade-offs in training neural networks. Here, the horizontal axis is the privacy loss budget on a logarithmic scale. The vertical axis is the accuracy loss. 0 would mean the model trained for privacy performs as well as the non-private model. Values close to 1 mean the private model has not learned anything. The results here for a neural network with 2 hidden layers show that there is a privacy utility trade-off, but even with privacy loss budgets up to epsilon 100, the accuracy loss is still substantial. If we're going by meaningful inference bounds, we want the privacy loss budget to be not much more than 1. There's no hard rule for what level of accuracy loss is acceptable, but it's hard to imagine many scenarios where it would be okay to give up a large amount of accuracy for privacy. So we're a long way from the region where we would need to be to talk about meaningful privacy utility trade-offs. But differential privacy guarantees are really strong. They cover all possible datasets, all possible attacks, and any leak that would allow us to distinguish between neighboring datasets. We can improve the theory to get tighter bounds, but maybe the problem is differential privacy is trying to make the wrong kinds of promises. At the other extreme, we can try to simulate actual attacks. This can reveal with high confidence when there's really a problem, and it can give us some sense of safety that at least the best known attacks today might not reveal anything that we're concerned about. But we need to be really careful about making any kinds of strong claims based on attacks, because attacks can only get better. For the rest of the talk, I'll focus on empirical results to understand the gap between what adversaries can actually infer from models using known attacks and attacks that we're developing, and what we can prove is impossible. I want to distinguish 2 classes of inference attacks. The first kind of attack learns about the dataset used for training. This is the most common setting, and it fits the definition of differential privacy well. The other kind of attack also starts from the model, but here the adversary is learning about the distribution the training data was sampled from, not necessarily learning about the particular training dataset. This may seem like a strange notion since the distribution itself is abstract, but I think it's an important one. In the extreme, if the model generalizes perfectly, it only captures the distribution and doesn't leak anything about the dataset. In practice, of course, we know this isn't possible, and the model is at risk of overfitting the training data, which is what enables dataset inference beyond what could be learned about just the distribution. We're going to talk about a few different examples of both distribution and dataset inference attacks, starting with membership inference. Membership inference is a dataset inference attack that attempts to reveal whether a model leaks the presence of a particular record in its training data. It is, so far, the most well-studied inference risk, mainly because it's the simplest. But there are other good reasons for studying it. It can pose a serious privacy threat. For example, if a model is trained on patients with some medical condition, membership inference could leak if a particular patient has the condition. It also is the simplest attack to define and measure, and has a direct link to differential privacy. Membership inference was formalized as a cryptographic game by Samuel Yam and colleagues. The adversary is presented with a model trained on some dataset D, and a record that is either in the training set, which we call a member, or from the same distribution. If the adversary can do better than random guessing in identifying whether or not the given record is a member, the model is leaking something about the dataset that it's trained on. In a generic membership inference attack, an adversary develops a prediction algorithm that takes a model and a candidate and outputs a prediction score that indicates the likelihood the candidate is a member. If the adversary starts with a pool of candidates, they need to set some threshold for that prediction for deciding if a given candidate is a member. The first prediction algorithm, introduced by Reza Shakri, was a meta-classifier. Meta-classifiers are really nice since you don't have to understand your problem to use them, just need a lot of compute cycles to train lots of models. But they also don't give you a lot of insights into why an attack works or doesn't work. Yam introduced a membership inference attack based on a much simpler idea. The intuition is that the training set members will have lower per instance loss than non-members, so it can be distinguished by just computing the loss function on the model's output. They set the threshold for distinguishing a member at the expected training loss of the model. To evaluate how effective these attacks are, we need to measure something that captures the attacker's goal. One common metric is membership advantage, the difference between the true positive rate and the false positive rate. If this is positive, the model is leaking something. But it doesn't tell us much about whether an adversary could do something useful with that leakage. A more realistic goal for an attacker is to determine for some candidates that they are members with high enough confidence to be actionable, which is better captured by the positive predictive value, PPV. PPV gives a much better understanding of how effective an attack is when the prior of the candidate pool is low, which is likely to be the case in cases that are most critical for privacy. The attacker has to pick some threshold for deciding when an input is a member to maximize some goal. For example, an attacker might have a maximum acceptable false positive rate and want to identify as many members as possible without exceeding that false positive rate. Here we can see the impact of privacy noise on the per instance loss values used by the Yam attack. Note that there is a huge privacy loss budget, but it still has a big impact on thwarting the attack. One surprising result here is that for an adversary with a low false positive rate threshold, the privacy noise actually helps. The minimum false positive rate for Yam on the non-private model is 0.1. Even for models with no privacy noise added, there doesn't seem to be a threshold that would allow an adversary to conduct a significant attack. The PPV never gets above 0.8, and it would take quite a ruthless adversary to harm someone based on that probability. So we need better attacks to achieve high PPV for some inputs. Our new attack is based on the intuition that members won't necessarily be at a global minimum in the loss function, which is the assumption behind the Yam attack, but that they are likely to be at a local minimum in the loss function if the model is overfitting to the training data. To test for this, we sample inputs around the candidate input and test if the loss increases or decreases. We call the number of times the loss of the sample around the candidate increases the Merlin ratio, and identify members by their high Merlin ratios. For the non-members, the Merlin ratios are distributed around 0.5, which is what we would expect for points that are not at local minima. For the members, we see the Merlin ratios skewed in a way that looks similar to the results for per instance loss for the Yam attack, but with a much bigger split at the far left of the graph. As we see here, a small amount of privacy noise does eliminate this tail, and makes the curves for members and non-members nearly indistinguishable. Here we see the trade-offs available selecting the threshold for the Merlin attack. This is for the non-private model. In comparison to the per instance loss attack, the attacker advantage is lower, but here there are thresholds available with very low false positive rate and high positive predictive value. If you know your Welsh mythology, you would expect if there's a Merlin attack, there has to be a Morgan attack as well. The hard part of coming up with this is needing to find something that matches the backronym correctly. Morgan combines the two attacks based on the observation that the local minimum test doesn't work at the extreme per instance loss points. So we need to set two thresholds, one for the absolute loss and one for the Moreland ratio. This allows us to identify a small region of candidates as members with very high PPV, above 95% for all the datasets. Membership inference is an example of a dataset inference attack. Next, I want to talk about a distribution inference attack. This is a very different kind of attack. Instead of learning about whether an individual record is in the dataset, the adversary is learning some global statistical property of the distribution the model was trained on. Here's an example to illustrate what we mean by property inference. Suppose there was a secret dataset of handwritten digits, and someone trained and released a model on that dataset for the task of recognizing the digits. The model is supposed to capture statistical properties of the distribution, but only ones relevant to the task it was trained for. So if an adversary could make use of the model to make a prediction about the fraction of the 7-digit samples in the training set that were written with slashes through them, that would be a surprising property to be able to infer from the model. This illustration might not suggest a serious privacy risk, but there are several examples that have been demonstrated where properties about data distributions that might be sensitive can be inferred from models. As one example, a model trained to detect crypto mining behaviors might reveal if the execution traces it was trained on were from machines that were patched for Spectre. I'm going to talk more about a few specific property inference attacks soon, but first I want to formalize the attack, adapting the cryptographic game formalization of the membership inference attack to property inference. Now the adversary's goal is to distinguish between two distributions. They are given a model trained on a dataset sampled by one of the two distributions, and need to predict which one of the distributions was used to train the model. Here are two examples showing how well an adversary can distinguish between two training distributions. For both examples, the property the adversary is inferring is the fraction of the training distribution that is female. On the left side, the task is to predict income based on personal characteristics on the US Census dataset. On the right side, the task is predicting age from hand X-ray images. The adversary is training a meta-classifier based on 4,000 models to distinguish between the two training distributions, and then making predictions for 1,000 unseen models. For distributions near 0.5, the predictions are better than guessing, but not by much. But for more skewed ratios, the predictions become quite accurate. We can infer properties other than just gender distributions. For a model trained to predict archive subject areas from a citation graph, we can infer the average degree of a node in the training distribution. Here we see the results of an experiment training models on graphs with differing average degree, constructed by either removing high or low degree nodes from the original training graph. A meta-classifier trained on 1,400 models can distinguish fairly accurately between models trained on graphs with different average node degrees. More interestingly, we can train a regression meta-classifier to predict the average degree of the training distribution used to train an input model, and quite accurately distinguish between different training distributions. Even when the average degrees differ by only one, the meta-classifier is able to distinguish them. This isn't a privacy risk for the archive dataset, but you can imagine many graph datasets, such as social network graphs or computer network graphs, where revealing global graph properties could be a problem. So we've seen an example of a data distribution attack that is quite different from a dataset inference attack. The final kinds of attacks I'm going to talk about appear to be quite similar, and there's been a lot of confusion because of uncertainty about whether an attack is actually a distribution inference attack or a dataset inference attack. For both of these attacks, the adversary has partial information about some record and wants to infer an unknown sensitive attribute. In an attribute inference attack, the adversary has a model trained on a dataset that includes the complete training record. The adversary's goal is to use the model to predict the most likely value of the missing attribute in the partial record. In a data imputation attack, the adversary's goal is the same, but here, instead of having access to a model trained on the particular data element, the adversary just has knowledge of the data distribution. It isn't obvious, though, when an attribute inference attack appears to work, if it really is because the model leaked the sensitive attribute from a training record, or if the model has really just leaked information about the distribution, which is what the prediction algorithm is using indirectly to make the prediction. I argue that an attack is only a meaningful attribute inference attack if the adversary is able to learn something from the model that they couldn't learn just from knowing the data distribution. If the data distribution is public, it doesn't matter if the adversary can learn about the distribution from the model, since they could learn about the distribution in many ways. If the data distribution is secret, then it does matter if the model reveals it, but that sounds a lot more like a property inference attack than an attribute inference attack. We'll explore this distinction using the US Census adult dataset. The task here is to predict whether someone will have a yearly income above $50,000 based on 14 provided attributes. One of the attributes is sex, which we know is not a binary attribute in reality, but is in the census dataset. For our attribute inference experiments, we treat sex as the sensitive, unknown attribute and consider an adversary who knows all of the other attributes for an individual and wants to predict the value of their sex attribute. The imputation model is trained on records from the distribution to predict a missing sex attribute from an input record with all the other features. It does pretty well. It can predict male with over 0.8 ppv. For attribute inference, we want to see if an adversary who also has access to a model can do better than the imputation adversary for records in its training set. The strategy we have is to use a hyperparameter to combine the two models, predicting the attribute that maximizes the probability. We tune the hyperparameter zeta to maximize some goal, such as ppv for the targeted attribute. Here we see the results when the goal is to maximize the ppv when predicting male. The low zeta value means that most of the information is coming from the imputation. We do see a small improvement in ppv here, so some additional information is coming from the model. But it turns out that the improvement is the same for members of the training dataset as it is for non-members. So what this suggests is that the model has learned and revealed something about the distribution that wasn't learned by the imputation model. When we maximize ppv for female, the zeta parameter is higher, indicating that there is more value coming from the trained model, but it has negligible impact on the quality of the predictions. So we've seen an example of an attack where the attacker's goal is the same, to infer a missing attribute, but the nature of the attack can either be on a data distribution or a training dataset. I want to close by returning to the theme of gaps between theory and practice. The differential privacy definition connects closely with the risks of membership inference and attribute inference, bounding the risk to an individual of contributing their data to a training set. But it doesn't capture many of the privacy risks associated with machine learning. With imputation, there's a risk that sensitive characteristics of an individual can be inferred even if they have not provided any personal data. So there is little an individual can do about this, but maybe there are things we can do as a society. With property inference, privacy noise probably helps, but there's no obvious connection with differential privacy, since it isn't about distinguishing neighboring datasets. I want to encourage this community to continue to do great work on formal privacy, but also to consider the limitations of the formal definitions we use, and the challenges of connecting privacy research to realistic threats. Thank you for the opportunity to speak. I look forward to your questions.